Welcome. Today, we're moving beyond basic machine learning and diving into the world of deep learning, a field that mimics the structure of the human brain to tackle the toughest challenges in technology. Deep learning has revolutionized how machines learn, making them capable of solving problems that were once thought impossible. As we journey through this video, you'll see how these advanced systems work, starting from the basics and building up to the most powerful AI architectures used today. Let's begin by understanding what makes deep learning so special compared to traditional machine learning. Learning is a specialized subset of machine learning. Unlike traditional ML, which relies on humans to manually engineer features, deep learning models can automatically discover features from raw data. The term deep refers to the multiple layers these models use to process information, allowing them to learn complex patterns and make accurate predictions. This ability to extract features on their own is what sets deep learning apart, making it the backbone of modern AI systems. As we move forward, you'll see how these layers work together to transform raw data into meaningful insights. The heart of deep learning lies the artificial neural network, or ANN. Inspired by the biological structure of the human brain, an ANN consists of thousands or even millions of interconnected nodes. These nodes work together to analyze data, find patterns, and make predictions. The design allows the network to learn from experience, improving its performance as it processes more information. This framework is what enables deep learning models to tackle tasks ranging from image recognition to language translation. Next, we'll look at the basic building block of these networks, the neuron. Neuron, also called a node, is the fundamental unit of a neural network. Think of it as a tiny mathematical calculator. Each neuron receives multiple inputs, multiplies them by specific weights, adds a bias, and then passes the result through an activation function. This process determines what signal the neuron sends forward. By combining the outputs of many neurons, the network can learn intricate patterns and relationships in data. Understanding how neurons operate is key to grasping the power of deep learning. Now, let's explore how these neurons are organized within layers. Neural networks are structured into three main types of layers: input, hidden, and output. The input layer is where raw data enters the network, such as the pixels of an image. Hidden layers are where the magic happens. These layers extract abstract features, with each layer building upon the previous one. For example, the first hidden layer might detect edges, the next shapes, and the next full objects. Finally, the output layer delivers the network's prediction, such as identifying an image as a car with high certainty. This layered approach is what gives deep learning its depth and power. Activation functions are like volume dials or light switches for neurons. They decide whether a neuron should fire or stay quiet. Without activation functions, a neural network would be nothing more than a giant linear equation, limited to solving basic problems. By introducing non-linearity, activation functions enable networks to learn complex, curvy patterns found in real-world data, such as human speech or facial features. This is a crucial step in making deep learning models versatile and powerful. Next, we'll look at the most popular activation function used today, ReLU. ReLU, or Rectified Linear Unit, is the most widely used activation function in deep learning. Its rule is simple: if the input is negative, it becomes 0. If positive, it stays the same. This approach speeds up training by turning off neurons that aren't contributing, allowing the network to focus on the most important features. ReLU's efficiency has made it the default choice for many modern AI models. As we continue, you'll see how other activation functions, like Sigmoid and Softmax, play unique roles in different types of networks. Sigmoid function takes any number and compresses it into a range between 0 and 1. Its output forms a curve, making it ideal for models that predict probabilities. For example, Sigmoid is used to determine whether an email is spam or not, assigning a probability to each outcome. This function is especially useful in binary classification tasks, where the answer is a simple yes or no. Understanding Sigmoid helps us see how neural networks make decisions based on probabilities, a fundamental aspect of many AI applications. Softmax is the go-to activation function for multi-class classification problems. Unlike Sigmoid, which handles yes-no questions, Softmax takes a list of raw scores and turns them into a probability distribution that adds up to 100%. For instance, it can predict the likelihood that an image is a dog, cat, or fox, assigning percentages to each possibility. This function is essential for tasks where the answer could be one of many categories, making it a cornerstone of advanced AI models. Now let's explore how neural networks actually learn. This is the most technical part of our journey, but it's crucial for understanding how models improve over time. Imagine adjusting dials on a radio or finding your way down a foggy mountain. These analogies help explain the process. Neural networks start with random guesses, but through training, they gradually refine their predictions. Two key concepts drive this learning: backpropagation and gradient descent. Let's break down how these work. Backpropagation is the method neural networks use to correct their mistakes. When the network makes a wrong prediction, it calculates the error at the output layer and sends that error backward through the network. Each neuron receives feedback on how much it contributed to the mistake, allowing its settings to be adjusted. This process is repeated over many cycles, gradually improving the network's accuracy. Backpropagation is the backbone of neural network training, ensuring that each layer learns from its errors. Gradient descent is the optimization algorithm that fixes the mistakes identified by backpropagation. Picture yourself on a foggy mountain, trying to find the lowest point. You look at the slope beneath your feet and take a step in the steepest downward direction. Gradient descent does this mathematically, minimizing errors and perfecting the model. By repeatedly adjusting the network's weights and biases, gradient descent ensures that the model becomes more accurate with each iteration. Learning isn't just about basic neural networks. There are specialized architectures designed for specific types of data and tasks. These advanced tools have unlocked new possibilities in fields like image processing, language understanding, and sequential data analysis. By tailoring the network's structure to the problem at hand, researchers have achieved breakthroughs that were previously out of reach. Let's explore some of these specialized architectures, starting with convolutional neural networks. Convolutional neural networks, or CNNs, are designed specifically for visual data like images and videos. Instead of analyzing an entire image at once, CNNs use small sliding filters to scan for low-level features such as edges, textures, and colors. These features are then combined to recognize full objects. CNNs have revolutionized fields like computer vision, enabling machines to identify faces, detect objects, and even drive cars. A unique structure makes them incredibly effective for image-related tasks. Current neural networks, or INNs, are built for sequential data where order matters, such as sentences or time series information. Unlike traditional networks, INNs feature internal feedback loops that allow information to persist, giving the network a short-term memory of what came before. This makes INNs ideal for tasks like language modeling, speech recognition, and predicting stock prices. Their ability to handle sequences sets them apart from other architectures. Short-term memory, LSTM, networks are a special type of INN designed to overcome the vanishing gradient problem. Standard INNs struggle with long-term memory, often forgetting important information over time. LSTMs solve this by adding memory cells and gates that decide what to remember, what to forget, and what to pass on. This makes them perfect for tasks that require understanding long sequences, such as language translation or music composition. Transformer models, introduced in 2017, have completely changed the landscape of AI. Unlike INNs, transformers use a mechanism called self-attention to analyze entire sentences at once, calculating how each word relates to every other word. This approach has enabled breakthroughs in natural language processing, powering technologies like ChatGPT and Gemini. Transformers are now the foundation of modern generative AI, making them one of the most important architectures in the field. Learning stands out as the dominant force in modern AI for several reasons. First, it scales with data, unlike traditional machine learning, which plateaus. Deep learning models keep improving as more data and computing power added. Second, it automates feature extraction, eliminating the need for manual data preparation. Finally, its unmatched versatility allows the same principles to be used for generating art, composing music, driving cars, and translating languages. This combination of scalability, automation, and versatility makes deep learning truly powerful. One of the most impressive aspects of deep learning is its scalability. As you feed more data and computing power into a model, its accuracy continues to improve. This is in stark contrast to traditional machine learning, which often hits a ceiling. Deep learning's ability to handle massive datasets has enabled breakthroughs in fields like healthcare, finance, and entertainment. The more data you provide, the smarter the model becomes, unlocking new possibilities for AI applications. Deep learning models excel at automated feature extraction. Unlike traditional approaches that require manual engineering of features, these models learn to identify important patterns directly from raw data. This automation speeds up the development process and reduces human error. By letting the network discover features on its own, researchers can focus on solving bigger problems, pushing the boundaries of what AI can achieve. Versatility of deep learning is unmatched. The same core principles can be applied to generate art, compose music, drive autonomous vehicles, and translate languages. This flexibility has made deep learning the foundation of countless innovations across industries. Whether it's creating realistic images or understanding complex speech patterns, deep learning adapts to a wide range of tasks, making it the go-to technology for modern AI. Input layer is where all neural networks begin. It receives raw data, such as the pixels of an image or the words in a sentence. This layer acts as the entry point, passing information to the hidden layers for further processing. By starting with raw data, the network can learn to extract features and make predictions, setting the stage for deeper analysis. Hidden layers are where the magic happens in neural networks. These layers extract abstract features from the input data, with each layer building upon the previous one. For example, the first hidden layer might detect edges in an image, the next shapes, and the next full objects. The depth of these layers allows the network to learn complex patterns, making deep learning models incredibly powerful. The output layer is the final destination in a neural network. After processing through multiple hidden layers, the network delivers its prediction, such as identifying an image as a car with high certainty. This layer translates the network's learned features into actionable results, making it the key to solving real-world problems. Activation functions introduce nonlinearity into neural networks, allowing them to learn complex, real-world patterns. Without activation functions, networks would be limited to solving basic linear problems. By applying mathematical formulas to neuron outputs, activation functions enable the network to handle tasks like speech recognition and facial analysis, making them essential for advanced AI. ReLU's simple rule, turn negatives to zero, keep positives unchanged, makes it an efficiency booster for neural networks. By shutting off neurons that aren't contributing, ReLU speeds up training and focuses the network's attention on the most important features. This efficiency has made ReLU the default activation function in many deep learning models. Sigmoid is perfect for binary decisions, compressing outputs into a range between 0 and 1. Its S-shaped curve makes it ideal for probability-based tasks, such as determining whether an email is spam or not. By providing clear, interpretable results, Sigmoid helps neural networks make accurate yes-no predictions. Softmax transforms raw scores into a probability distribution, making it essential for multi-class classification problems. By assigning percentages to each possible outcome, Softmax enables neural networks to handle tasks where the answer could be one of many categories, such as identifying animals in images. Backpropagation is the process that allows neural networks to learn from their mistakes. By calculating the error at the output layer and sending it backward, each neuron receives feedback on its contribution to the error. This iterative process ensures that the network improves its accuracy over time, becoming smarter with each cycle. Gradient descent is the mathematical method used to perfect neural network models. By taking steps in the direction of steepest descent, the algorithm minimizes errors and optimizes the network settings. This process is repeated until the model reaches peak performance, making gradient descent a cornerstone of deep learning. Convolutional neural networks are experts at processing visual data. By using sliding filters to scan images, CNNs detect low-level features like edges and textures, building up to full object recognition. This specialized architecture has enabled machines to excel at tasks like face detection, object tracking, and autonomous driving. Current neural networks are designed to handle sequences, making them ideal for tasks where order matters. By using feedback loops, RNNs maintain a short-term memory of previous inputs, allowing them to process sentences, time series data, and more. Their unique structure sets them apart from other neural networks. LSTM networks solve the long-term memory problem faced by standard RNNs. By adding memory cells and gates, LSTMs decide what information to remember, forget, or pass on. This makes them perfect for tasks that require understanding long sequences, such as language translation and music generation. Transformers have revolutionized AI by using self-attention to analyze entire sentences at once. This architecture powers modern generative AI, enabling breakthroughs in natural language processing. Technologies like ChatGPT and Gemini rely on transformers, making them the foundation of today's most advanced AI systems. Deep learning isn't just for technical tasks, it's also used to generate art. By learning patterns in images and styles, neural networks can create stunning visual pieces, pushing the boundaries of creativity. This application showcases the versatility and power of deep learning in fields beyond traditional AI. AI-powered deep learning models can compose music by learning from vast datasets of melodies and rhythms. These models generate original compositions, blending creativity with technology. The ability to create music demonstrates how deep learning adapts to diverse fields, inspiring new forms of artistic expression. Deep learning is at the core of autonomous vehicles. By processing visual data from cameras and sensors, neural networks enable cars to recognize objects, navigate roads, and make real-time decisions. This technology is transforming transportation, making self-driving cars a reality. Deep learning models excel at translating languages. By understanding complex patterns in text, these models can convert sentences from one language to another with remarkable accuracy. This capability is essential for global communication, breaking down barriers and connecting people worldwide. Healthcare deep learning is used to analyze medical images, predict patient outcomes, and assist in diagnosis. By learning from vast datasets, these models help doctors make better decisions, improving patient care and saving lives. The impact of deep learning in healthcare is profound and growing rapidly. Deep learning is transforming finance by analyzing market trends, predicting stock prices, and detecting fraud. These models process massive amounts of data, uncovering patterns that humans might miss. The result is smarter, faster financial decisions that drive innovation in the industry. AI-driven deep learning models are used in entertainment to recommend movies, generate content, and personalize experiences. By understanding user preferences, these models create engaging and tailored entertainment options, enhancing enjoyment and satisfaction. Despite its power, deep learning faces challenges such as data requirements, computational costs, and interpretability. Researchers are working to address these issues, making models more efficient and understandable. Overcoming these challenges will unlock even greater potential for AI. Future of deep learning is bright, with ongoing advancements in architectures, training methods, and applications. As models become more powerful and accessible, AI will continue to transform industries and improve lives. Staying informed about these developments is key to understanding the evolving world of technology. You've covered the mind-bending world of deep learning, from neurons and layers to advanced architectures like transformers. These technologies power today's most powerful AI systems, enabling breakthroughs across industries. Deep learning's scalability, automation, and versatility make it the dominant force in modern AI. Thank you for joining this deep dive into deep learning. We explored everything from basic neurons to the revolutionary transformer models. Stay tuned for more in this fundamental series as we continue to unravel the mysteries of AI and technology. See you in the next video.